Lecture 9, Part 1 on Soil Water, Unsaturated Zone Hydrology. GO2 4203 students, welcome. Now you are all familiar with groundwater. I will build upon that. Also for the master's students of the programs Earth, Surface and Water or Water Science and Management, who may also be watching these lectures as part of their first week introduction to GO4 4417 Unsaturated Zone Hydrology. First of all, welcome to you all, also on behalf of the course coordinator, Professor Mark Bierkens, to my left. Students, you have attended the master's course Principles of Groundwater Flow or the bachelor course GO2 4203 Physical Hydrology or both. So you are familiar with groundwater and I will build upon that. Good luck. This figure shows the unsaturated zone to be part of the soil situated between the soil surface and the water table or phreatic level, where some of the spaces between the soil particles are filled with air. The soil consists of solid substances, the matrix, and interstices or the pore space. As a complicating factor, there is usually air in the pores. Therefore, this zone is called the unsaturated zone, unsaturated meaning not saturated with water. An alternative name for the unsaturated zone is the vadose zone, or sometimes the zone of aeration, and the water stored there is called soil water. Part of the unsaturated zone are the root zone, which is part of the soil surrounding the roots of plants, the percolation zone, which is the zone where water moves in the direction of the water table, the capillary fringe, the fringe above the water table where water is sucked into pores by capillary forces and/or other forces. The vertical water flow at different depths in the unsaturated zone can be downward, infiltration from precipitation, percolation, and recharge of the groundwater, or upward, capillary rise, and evaporation that includes transpiration. The unsaturated zone can be temporarily saturated, but usually it's not. Soil water can be considered as important in many ways. With regard to land degradation processes, the photo to the left shows that if on a hill slope the precipitation intensity is larger than the infiltration rate into a soil, overland flow and gully erosion can occur. Too much water in a soil can cause mass movement. The photo to the right shows a hummocky appearance of a hill slope due to small mass movements, so-called soil creep. The relation between soil water plant and atmosphere is important for natural vegetation, agricultural practices, and in relation to climate change effects. The soil is important with regards to the recharge or replenishment of the underlying groundwater. Also, importantly, soil water provides a first line of defense against groundwater pollution from pathogenic bacteria and viruses. Within soil pores, forces act on the interfaces of the solid soil matrix with the water or at the air-water interfaces. Especially when a soil becomes drier, bacteria and viruses at these interfaces may be ripped apart, thereby inactivating, killing these bacteria and viruses. The soil consists of matrix, minerals and organic matter, and in the pores water and usually air. Minerals are substances that are formed naturally in the earth. They are usually inorganic and have a crystal structure. Organic matter is composed of organic compounds that have come from the remains of organisms such as plants and animals and their waste products in the environment. The minerals in a soil can be described by their size or soil texture. A micron is a thousandth of a millimeter, thus 1/1,000,000th of a meter. Sand has a size of 50 to 2000 micron. Silt is 2 to 50 micron and clay smaller than 2 micron. Sand can be subdivided into coarse sand and fine sand. Larger than 2 millimeter is gravel or rock. If we compare the size of a sand grain to a weather balloon, then a silt particle has the size of a basketball and a clay particle the size of a rice grain. But watch out, clay has a laminated structure and not a granular structure, as this comparison may seem to suggest. The porosity N of a soil is a measure of the pore spaces in a soil. It is the fraction of the volume of pore spaces over the total soil volume, usually in cubic centimeter per cubic centimeter, thus dimensionless between 0 and 1, or as a percentage between 0 and 100%. The porosity is the maximum volume fraction of water in a soil. It is the maximum volumetric moisture content of a soil and therefore also presented as theta S here. The S stands for saturation. Typical values for different types of soil are as indicated here. It is hard to perform hydrological tests on clay, as these may swell or shrink depending on the moisture content, and also on peat because of its high porosity. Please note the large range of porosity values for different types of soil given in brackets, and the large average value for the porosity N of clay as compared to sand. The soil's ability to retain water is strongly related to particle size and pore size. Water molecules hold more tightly to the fine particles and pores in a clay soil than to the coarser particles and pores of a sand, especially a well-sorted sand, so clays generally retain more water. The average porosity N for sand is lower than for clay. Sand has large grains that are closely packed, and in a well-sorted sand, one predominant pore size due to the predominant grain size is shown here. Sand has a granular structure with much water held in pores between the grains by capillary forces, whereas clay minerals have a laminated structure as shown here. Due to their mineral structure, small sheets of silicon oxide tetrahedrons and aluminium hydroxyl octahedrons, clay minerals are negatively charged at their surface. The mineral's negative charge is neutralized by cations, positively charged ions, such as sodium plus and calcium 2 plus, in the soil water. Thin films of water and neutralizing cations adhere to the clay mineral surface by electrostatic forces, and the same amount of water is held more strongly in clay than in sand, which is also why a sand layer in the subsurface can be quite permeable and clay and mudstone are not, why it is easier to remove water from a sand than clay layer, and why sand layers in the subsurface constitute the aquifers and clay layers the aquitards. The positive news that I can already tell you is that we need not worry too much about the exact forces with which water is bound to the soil matrix in the unsaturated zone, as we have a unifying concept for this, which is the concept of negative pore water pressures in the unsaturated zone when we take the existing air pressure at the water table as a reference or zero level. I will come back to this shortly. The volumetric moisture content theta is the fraction of the volume of moisture or water over the total soil volume, usually in cubic centimeter per cubic centimeter, thus dimensionless between 0 and 1, or as a percentage between 0 and 100%. The volumetric moisture content is usually determined from a stainless steel core sample ring or Kopecky ring as shown in these two photos. Collecting a good sample is an art in itself, which can best be explained in the field. Make sure that after collecting your sample, you immediately seal the ring using the plastic caps and some tape, so as to make sure that no moisture can escape from the sample. The rings have an inner diameter of 5 cm and a length of 5.1 cm, and thus a sampling volume of 100 cubic centimeter. Measure the soil sample mass MW. Saturate the sample and measure the soil sample mass again. This delivers MS. Dry the soil sample 24 hours in an oven at 105 degrees Celsius. Measure the soil sample mass again. This delivers MD. If V is the volume of the soil sample ring, the volumetric moisture content of a sample as taken from the field is then given by this equation, and the maximum volumetric moisture content at saturation, theta S, by this equation. Because the density of fresh water, rho W, is 1 gram per cubic centimeter, a difference in mass of 1 gram of water conveniently equals a difference of a volume of 1 cubic centimeter of water. To account for this in the equations, the density of water, rho W, has to feature in the denominators of these equations. Also, because the masses in the numerator of these equations are subtracted from one another, you can simply determine these masses within the core sample ring, that is, with the mass of the core sample ring itself included. Thus, the volumetric moisture content, theta, is the volume of water over the total soil volume in cubic centimeter per cubic centimeter. Some other soil moisture characteristics are the gravimetric moisture content, or wetness W. This is the mass of water over the mass of solid matter in gram per gram. And the relative moisture content, or wetting phase saturation, is defined as the fraction of the volumetric moisture content over the porosity. Finally, a much used soil physical characteristic in soil water hydrology is the soil bulk density, or dry bulk density, rho D, which is defined as the mass of a dry soil divided by the total soil volume in gram per cubic centimeter. Further to this, for the GO4 4417 students, the density of the solid fraction of a soil is defined as the mass of solids divided by the volume of solids. For a typical mineral soil, this density of the solid fraction can be taken as 2.65 gram per cubic centimeter. This is close to the density of quartz, generally the most prevalent mineral in the coarse fraction of a mineral soil. This sheet introduces some typical calculations for the soil water zone. The effective porosity Ne is the volume fraction, or percentage of soil or sediment that participates in the water flow process, thus excluding dead-end pores. When 10 mm of rain enters a soil with an effective porosity Ne of 0.4 and a volumetric moisture content of 0.3, there is 0.4 minus 0.3 is 0.1 pore space available, and the water will in first instance reach a depth of 10 divided by this 0.1 is 100 mm. The infiltration volume flux density, or infiltration rate, equals 10 mm per the time of infiltration, whereas the effective velocity equals 100 mm per the time of infiltration. Also, with reference to compaction of soils, think for instance of the compaction of polders due to the pumping out of water or otherwise draining of the land. A soil which, due to compaction in volume of pores, recedes from a porosity N from 0.43 to 0.37, loses in the upper 100 mm 0.43 minus 0.37 is 0.06 times the upper 100 mm, is 6 mm of storage capacity. You should thus think of the length units of millimeter as representing volumes of water. In actual fact, volumes of water per unit surface area perpendicular to the vertical infiltration process. Hydrostatics is the study of the forces in the soil-water system when there is hydrostatic equilibrium. This means that all forces are in equilibrium. There is no vertical water flow due to infiltration, percolation, or evaporation. In groundwater, as shown before, water does not per definition have to flow from a higher to a lower location. In the soil-water zone, a similar notion. Water does not per definition have to flow from a wetter part to a drier part of the soil. This is because you also need to take the elevation difference into account. I will come back to this later. Hydrostatic equilibrium means that the fluxes, the rates in the soil are zero and that the moisture content, the state, does not change. The moisture content differs at different depths. Again, I will come back to this later. The forces in the soil, to name a few, are gravity at high water contents in the soil for the larger pores, capillary forces, especially when the soil is dry in silt or sand. Adsorption, this is a process whereby soil water accumulates on solid soil surfaces, forming a thin molecular film of water when the soil is dry. Electrostatic forces in clay, osmotic pressure in saline soils, etc. However, as mentioned before, we as hydrologists need not worry too much about the exact forces with which water is bound to the soil matrix in the unsaturated zone, as we have a unifying concept for this, which is the concept of negative pore water pressures in the unsaturated zone. For this, we need to take the existing air pressure at the water table as a reference or zero level. Let's take a better look at this concept. And let's start off with groundwater first. Because we take the existing air pressure at the water table as a reference or zero level, the pressure head at a water table that can establish itself freely is defined as zero. When we apply this for groundwater under hydrostatic conditions, that is, no vertical water flow, and take the water table as a reference level, we can draw this figure. In this figure, the elevation of the groundwater in length units is given along the vertical axis. The energy levels of the hydraulic head, elevation head, and pressure head, also in length units, are given along the horizontal axis. The horizontal axis thus has a double meaning. It gives the energy levels, and the axis is positioned at the level of the water table. As the water table is taken as the reference level, the elevation head at the water table is 0 meters. As mentioned before, the pressure head at the water table is 0 meters. Then, according to Bernoulli's law, the hydraulic head equals elevation head plus pressure head. The hydraulic head at the water table, being the sum of elevation head and pressure head, equals 0 meters. When we descend into the groundwater, the elevation head decreases with the same amount in length units in which elevation in length units decreases. As the water table is taken as reference level, elevation heads below the water table are negative, and the relation between elevation head and elevation can be drawn as a line under an angle of 45 degrees for equally scaled axes as shown. When we descend into the groundwater, the pressure head in length units at different elevations in length units is linearly related to the length of the water column above the elevation of interest. Pressure heads below the water table thus are positive, and the relation between pressure head and elevation can now also be drawn as a line under an angle of 45 degrees for equally scaled axes, but in a different direction as for the elevation head, as shown in this figure. So when we move 0.1 meter below the water table, the pressure head equals 0.1 meter and the elevation head minus 0.1 meter. The hydraulic head equals 0 meter. When we move 1 meter below the water table, the pressure head equals 1 meter and the elevation head is minus 1 meter. The hydraulic head equals 0 meter. As the hydraulic head everywhere equals the sum of elevation head and pressure head, the hydraulic head in the saturated zone at all elevations equals 0 and thus is independent of elevation. As there are no differences in hydraulic head with elevation, there is no groundwater flow in the vertical, which is in agreement with our starting point, which was hydrostatic equilibrium, that is, no vertical groundwater flow. Now let's extend the hydrostatic equilibrium, no vertical water flow, into the unsaturated zone. What would a similar graph on the hydrostatic equilibrium conditions, no water flow, look like in the unsaturated zone, the zone above the water table? The soil pores then generally contain both water and air. In the unsaturated zone, as a consequence of Bernoulli's law, also the total energy, or another word for this is total potential, equals the sum of elevation head and pressure head. When we continue to take the water table as reference level, the elevation head at the water table remains defined as 0 meters. When we move upward from the water table, the elevation head increases with the same amount in length units in which the elevation above the water table, also in length units, increases. In order for there to be no water flow, the total potential in the unsaturated zone should remain 0. This can only be achieved if the pressure head above the water table decreases with the same amount in which the elevation above the water table increases, as shown in this figure. Thus, by defining the pressure head at the water table as 0, same as for groundwater, water pressures in the unsaturated zone are negative, that is, less than the existing air pressure. When we move 10 centimeter above the water table, the elevation head equals 10 centimeter and the pressure head equals minus 10 centimeter. The total potential is 0 centimeter. When we move 100 centimeter above the water table, the elevation head equals 100 centimeter and the pressure head equals minus 100 centimeter and the total potential 0 centimeter. Because pores in the unsaturated zone usually contain air, the total energy or total potential cannot be as easily determined as under the water table in the saturated zone, where it may simply be determined as the hydraulic head in a piezometer. In part because of this, a different term is used, namely the total potential or hydraulic potential. From an energy point of view, this term is fully equivalent to the term hydraulic head as used in the saturated zone. Also, for the elevation head and pressure head, other terms are used in the unsaturated zone. Gravitational potential is the equivalent of elevation head, and matrix potential is the equivalent of pressure head. Note that the matrix potential is the pressure head with a negative sign. In hydrology, the term suction is often used. Suction is the absolute value of the matrix potential, thus the matrix potential without the negative sign. A low suction thus means a slightly negative matrix potential, whereas a high suction indicates a strongly negative matrix potential. Bernoulli's law for the unsaturated zone can now be written as H equals Z plus psi, where H is the total potential in centimeter, Z is the gravitational potential in centimeter, and psi is the matrix potential in centimeter. For most practices and purposes, it suffices to consider the total potential H as made up of a gravitational potential Z and a matrix potential psi when dealing with unsaturated water flow through the soil matrix. However, in specific instances, other potentials may also be important, such as the pneumatic potential when air is entrapped in the soil, or the envelope potential caused by overburden pressure from overlying soil. Also, the osmotic potential may sometimes be an important potential to consider, for instance in irrigation, the addition of water to dry soils. Osmosis is a natural process that causes water to move from locations with a low solute concentration to locations with a higher solute concentration, in an attempt to rule out existing concentration differences. Osmotic potential, like the matrix potential, is negative. In dry conditions, it acts to draw water into the soil and lower the mechanical energy. This figure combines hydrostatic equilibrium in the saturated zone with hydrostatic equilibrium in the unsaturated zone and summarizes the terms used in both zones. In the former figures, which are named potential diagrams, the water table has been taken as a reference level or zero level for didactical reasons. Should another level, for instance the land surface, have been taken as reference level, this would only have affected the position of the gravitational potential or elevation headline and the position of the total potential or hydraulic headline, in the sense that both lines would shift to positions parallel to their current positions. Because the matrix potential or pressure headline remains locked in its present position, choice of a reference level does not influence the shape of a total potential or hydraulic headline or curve. One may therefore always simply choose the reference level that comes in most handy. Of course, once a level is selected for describing the energy levels at a specific location, one should stick to it. In fact, as the water table moves up and down, in practice it is better to take the land surface as reference level for the elevation head and gravitational potential. In the answer to the exercise 4.8.6 at the end of my book, the potential diagrams for both reference levels are compared. The dashed lines are for the water table as a reference level. As evident, and as it should be, it has no bearing on the calculations. This is a summary of the terminology used in potential diagrams in both English and Dutch for both groundwater and soil water. In groundwater, H is the hydraulic head, stijghoogte, Z is the elevation head, plaatshoogte, P divided by rho G is the pressure head, drukhoogte. Measurements are in meters. In soil water, H is the total potential, hydraulische potentiaal, Z is the gravitational potential, zwaartekrachtpotentiaal, and psi is the matrix potential, matrixpotentiaal, vochtspanning. All measurements in soil water are in centimeters. For the GO4 4417 unsaturated zone hydrology students, my book deals with the basic laws of hydrology, first of all in the groundwater compartment, as these laws are most easily explained for groundwater. In these lectures on soil water, we will be extending our knowledge and findings into the unsaturated zone. I have used lowercase or small h for hydraulic head in my book, as is customary in groundwater hydrology, and I will continue to use this for the total potential, the equivalent of the hydraulic head in the unsaturated zone. However, in books dealing predominantly with the unsaturated zone, it is customary to use uppercase or large H for the total potential and lowercase or small h for the matrix potential, and this will also be the case, with the exception of these introducing video lectures on soil water, for the GO4 4417 unsaturated zone hydrology course. The differences are as listed here.